In movies, surviving a gunfight looks simple. You grab the heaviest piece of metal you can find, duck behind it, and wait for the shooting to stop. Basic physics supports the core idea. If you place a solid steel plate in front of your body, it will stop a high-velocity projectile from piercing your skin. But a flat sheet of metal has a mechanical flaw. It lacks any support points to help distribute the brute force of that incoming impact. Without a way to manage the kinetic energy, you are left wrestling with a heavy, awkward slab of steel. It makes you sluggish and leaves you vulnerable to follow-up shots. Stopping the bullet is only the first hurdle. To actually survive, you have to mitigate the physical impact of the strike without sacrificing your ability to move. To fix the maneuverability issue, you have to rethink the ergonomics. You start by adding a non-slip grip to the back of the shield, along with secure arm straps and a sturdy shoulder rest. These three components align to form a triangular stability system. This framework locks the heavy plate to your body. By distributing the weight across the arm and torso, the shield remains stable while you are free to pivot and advance. Explosive shockwaves introduce a different level of threat. Unlike a localized bullet strike, a blast wave hits the entire shield surface with massive, uniform pressure. When that wall of pressure hits a standard flat panel, the metal can buckle instantly. It deforms or fractures, losing its integrity when you need it most. Since the shield is now strapped firmly to your body, a buckling or shattering plate becomes a lethal hazard. Solving this requires a complete overhaul of the shield's internal structure. To resist these forces, you embed a skeleton of thick parallel reinforcement bars directly into the core. When a blast hits the exterior, these bars catch the impact and disperse the energy across the entire panel, preventing the center from snapping under pressure. However, physics dictates that the energy must go somewhere. The metal bars save the shield from breaking, but that immense kinetic force travels straight through the armor and into the person holding it. This unmitigated transfer leads to severe blunt force trauma, internal injuries, and broken bones. To protect the human operator, you must integrate a specialized high-toughness cushioning layer on the inner face of the panel. This internal padding acts as a final decelerator. It compresses to absorb the remaining shockwave energy, reducing the force to a level the human body can actually tolerate. A successful shield must protect both the steel and the flesh. Structural integrity is useless if the kinetic transfer kills the operator inside. At this point, you have an impenetrable, cushioned wall. But by building it large enough to cover your torso and head, you've effectively blinded yourself to the threat. In a fast-moving firefight, losing situational awareness is just as dangerous as the bullets themselves. The solution is a viewing window integrated into the upper portion of the shield. To maintain protection, this window uses multiple layers of transparent, vibration-damping, bulletproof materials. It has to be as tough as the metal surrounding it. Restoring clear vision without creating a structural weak point is the final step in maintaining an aggressive defensive posture. Finally, you add tactical lights, laser interfaces, and modular mounts. To the exterior of the window, this transforms the object from a raw slab of steel into an illuminated, multi-layered, technologically integrated system. By solving each mechanical flaw, the design has evolved from a passive piece of cover into an active tool for protection. The modern bulletproof shield succeeds through its engineering of the human-machine interface. By balancing weight, kinetic dissipation, and sensory input, it allows an operator to survive conditions that would otherwise be fatal.